Hello and welcome to our presentation on emerging properties in self-supervised vision transformers, a paper that was published in ICLR 2021. My name is Jacob P, and I am joined by Jacob O, Sharon, and Tristan. For an overview of what our project is going to go over, we're going to start off with an introduction, going over the main thesis of the topic. Then we're going to go over the related work that is paramount to understanding our actual paper. Then we're going through the models, the author's model architecture. And then we're going to go through the actual implementation of the model, as well as some key figures. And then finally, we're going to go over the results. So for an introduction, as we should know by now, hopefully, vision transformers have emerged as a solution for common computer vision tasks. Before that, a common use of transformers was with natural language processing, or NLP. And some of these NLPs, such as BERT and GPT, have relied upon self-supervised learning. Self-supervised learning has also been used to with ComNets. So the goal of this paper is to combine self-supervised learning with these vision transformers in order to obtain good feature maps of images. And the attempt to do this with knowledge in distillation with no labels, aka Dyno. To see Dyno in action, here we have an image here of a giraffe, and here we have the self-obtained feature map of a giraffe. Dyno doesn't only just work with images, however, it also works with videos, as we can see from this video from the Meta AI, formerly known as Facebook AI. We can see the feature map image of this boat, for example, and as the waves go up and down, the feature map of the boat will change. We're going to see the feature map, more of the boat will be shown. So for related topics, there are two key topics that we're going to go over. First of all is self-training and knowledge distillations. And then we're going to go over self-supervised learning. For self-training and knowledge distillation, I'm going to keep this brief because papers such as DITE have gone over this in far more detail. But just to re-go over everything, self-training is propagating a small set of annotations to a large set of unlabeled instances. This could be done with either hard labels, which are binary, either it's not labeled something or it is labeled something, or with a scale of 0 to 1, where the higher the number is, the larger of a chance it could be to be this label, and it could be multiple labels at the same time. And assignment of soft labels is often referred to as knowledge distillation. And the goal of this paper is to extend knowledge distillation to data with no labels. Speaking of no labels, self-supervised learning, to keep it brief, learning from unlabeled data. An example of something that does this is a model that is something that trains a model by discriminating images with data augmentations. What do I mean by this? Let's take an image A, an image of the giraffes again, and let's compare it to an image B, an image of an airplane. So with taking two segments of this image, we can see that both images feature a sky, so that's probably not a key feature. However, this image right here features more of the giraffe's head and neck, so that might be considered more of a key feature. This training could have a few problems. It either requires, you're either comparing it to every image, which would take forever, or comparing it would have to have a large batch size. So to kind of solve this issue, recently it has been found that unsupervised features can be learned without discrimination. And this is done by comparing different data augmentations of the same image. So we have the same image A here, and we're going to compare it to that same image with a different data augmentation. In this case, this has been turned 180 degrees and has also been mirrored. And that way is another way to compare to obtain feature maps of the same image by only using the image itself. A good model that does this is Bootstrap Your Own Latent, or BYOL. We'll just go over this architecture real quick. We have an input image X, which we're going to then spawn two different data augmentations of it to get this view. And then we're going to run that through a ResNet with two different weights, the original training weights, and then weights that are obtained from this weight using a exponential moving average, or EMA, to get the representation. Then we're going to run an MPL using, again, EMA to obtain these weights from these weights to get a projection. And then finally, for the two different architectures, this one's just going to stop. And this one is going to have another MPL to obtain the prediction. And then using an MSE loss function, it's going to connect to the target and to try to predict the target try to predict the actual features. So why did I go over BYOL? It's because if we look at BYOL and compare it to Dyno, we can see that Dyno has been directly inspired from BYOL. We can see similarities in start with the target image, split off into two data augmentations, have a general similar architecture style. However, there are two key differences. The first is that for the online and student for BYOL, that is the only one with prediction. However, for Dyno, the architectures are the same, so they both have a prediction layer. And secondly, is the loss function. In Dyno's case, instead of MSE, we use cross entropy layer. Now that we have seen the model, I'm going to pass it on to Jacob O, and he's going to talk about the model in more detail.
All right. So I'm going to go through a quick overview of the network. So as Jake laid out, we're going to start off with two separate augmentations of the same image. These will get passed into a student and teacher network. And then after some centering and softmax, and I'll explain what the purpose of these are in a bit, we will get some encoded vectors, and we can compare to make sure these two vectors are similar using the cross entropy. So first off, for self-distillation, we need to have a teacher network. So where exactly does this teacher network come from in our model? So typically, if we're using a teacher-student model, we're going to have a very large network that's already been pre-trained and is just trying to teach the student model what kind of features to extract. However, in our case, we don't really have a pre-trained network to teach our model, our student model. So how do they overcome this? They actually take many models and they're going to average them together to make a single teacher model. And the way they do this is they're going to take the student model through different epochs, and they're going to keep an exponential moving average of the parameters. And by averaging these parameters, they get much better results than just using a single student model. And so to get the teacher's parameters for the next epoch, you'll put a certain amount of weight on the current parameters and the inverse amount of weight on the next iteration for the student. As a result, the teacher model typically gets its much better results, and we can treat it more so like a ground truth for the student to learn off of. As for the augmentations that we pass into each student, the augmentations that we pass into the student and teacher are going to be different. Because we want the teacher to be more so the ground truth, we're going to give it more global context. Meanwhile, the student is going to get a mix of local and global contexts. So what does that look like? So the teacher is always going to get global context. So something like this red image, where we're going to crop out more than 50% of the image. So the teacher always has a pretty good understanding of what the original image was. In contrast, the student might get a local crop, something like this blue image, which you can see is less than 50% of the image. So as we pass these two separate crops in the student teacher, this student, given much more local context, is forced to create some guesses as to what the global context of the original image was. So we're getting some local to global correspondence here, which results in much better features being extracted. As for the feature vectors that are extracted, let's take a look at one we might get. So if we had a 5-dimensional vector we were trying to extract from both of them, it might look something like this. I'll represent them with a graph. So from here, we apply cross entropy to see how different they are. One problem, though, with this approach is that the student and teacher models might get a little tricky. Say the student and teacher both predict the uniform distribution. So the teacher and student both output the same uniform distribution. If we apply cross entropy on two uniform distributions, we'd get a loss of 0, which means the student and teachers are doing perfect, we think. But there's actually no useful features being extracted here. Same thing if the student and teachers output the same particular value every single time, the same dimension. They're going to think they're doing perfect, but we're not getting any useful information out of this. So we need to avoid this collapse between the student and teacher. And this is done using two methods. The first is temperature. So say we have a distribution and we want it to be less uniform. We can sharpen the results by using the temperature feature. And what this does, it takes whatever the current peak is, the current mode, and it's going to exaggerate it while suppressing everything else. So we end up with a much more peak distribution that's farther away from a uniform distribution. So practice, it will look something like this. We're going to take the softmax function, and we're going to divide every value by a predetermined temperature hyperparameter. And what this does, it expresses every value except for the highest value or the mode. Another problem we need to deal with is peaked distributions. So if the teacher and student output the same value every single time, we can avoid that using centering, which forces the distribution more towards the uniform distribution. So we can keep a running average of each value. So say that the average value in this column is typically around this yellow bar. what we're going to do is we're going to push all the values towards the center, and we get a more uniform distribution. So how do we keep these centers? How do we keep these centers? What? Slightly out of order, I apologize. The center, we can see we could put a current value on the current center, and we calculate the average for the next batch that's getting passed in. So the center is getting updated with each batch we pass in. And what the center ends up being is just a bias that we apply to the output of a model. So this bias avoids the problem with having peaked distributions. So the balance between these two factors, temperature and centering, one of them is avoiding peaked, one of them is enforcing, one of them is avoiding uniform, is very hyperparameter sensitive. So applying this kind of approach to different data sets might require specific hyperparameter tuning. That's one of the problems with the approach. But overall, the authors were able to balance these and get very good results. All right, I'll pass it on to Sharon to talk about the implementation details.
Okay, so I'll start us off with some implementation details, and then we'll talk about how we evaluate the model. So first, the transformer is exactly equal to DIT. You can see the details here. You can see model blocks, dimension heads, number of tokens, number of parameters, and throughput. And there's two types of models here, VIT-S and VIT-B. And then we have a number here that represents the size of the image patches. N by N is the size of the image patches, so we use N equals 16 and N equals 8, depending on the model. Okay, next, we append a learnable class token to the sequence of image patches. It does not come with label supervision or supervision. It starts off empty, and it is learned over time by the model. Then we pre-train on ImageNet without labels. We use Atom W optimizer. Batch size is 1024. Learning rate is 0.005 times the batch size divided by 256. Weight decay follows cosine schedule from 0.04 to 0.4. And the data augmentation that is used in the paper is color jittering, Gaussian blur, solarization, and multi-crop. Okay, so now how do we evaluate the model? We're learning some set of features, and we want to see if they're good, if we're categorizing them well, and so on. One way in which this has been done in the past is by learning a linear classifier and frozen features. This is a common way to check your feature space. Commonly, we perform this type of data augmentation that includes random resize crops and horizontal flips. And the logic here when we're learning a linear classifier is that if our feature space is well behaved, then it's possible for us to get a linear classifier that can split and decide and classify the features based on one way or the other. So the accuracy of the linear classifier is represents the behavior of our feature space. In this paper, they find a new method that can also be used to evaluate, which works particularly well with Dyno. So first they freeze the pre-trained model and store features of trained data on the downstream task. Then they match image feature to the k nearest feature and k equals 20. So really they use, instead of a linear classifier, they use a k nearest neighbors classifier approach similar to it. And this works particularly well in this paper and is one of the main results that they want to show. And you can see here. So here we have an animation of the features being learned over time. So as you can see, they all start here randomly, and then over time, as the epochs go up and the model is trained, the features separate into different clusters. And we can see based on the colors that the clusters are very nicely contained. So here I'll stop it just to highlight it. So here we can see, for example, the canine cluster is all pretty well done. So from this, we can conclude that with a transformer model and the Dyno method, then we're able to get features that are neatly clustered together. This is a property that this has shown up for the first time. And note, this is a visualization, so the model is not given these labels themselves. They're added after the fact for the visualization purpose. Okay, so results. The results reported in this paper are run by the authors. So that's one thing to keep in mind. They had to do this because they have come up with this KNN type of classifier to check the accuracy. So that's new. So other people haven't done this. So they performed this KNN evaluation for models with the other models' official released weights. And going into it, we can see comparison with the same architecture. So these are different self-supervised learning methods on ResNet 50. And they have equal parameters and throughput, so they are directly comparable. And we can see that Dyno can achieve equal linear scores and slightly better KNN scores. But the point here isn't with the ResNet 50. With the ResNet 50, the KNN score is slightly bigger. But the real result that we can see is what happens when we add a VIT. When we add a VIT for other self-supervised methods, the KNN score is around the same area. And the linear score is slightly better. But for Dyno specifically, we get a huge increase in this KNN scoring. So as far as k-nearest neighbor classifier, with the transformer, Dyno is able to get a very impressive result. Next, and the last thing I'm going to talk about is comparison with different architectures. These architectures are not directly comparable. You can see they're different sizes and so on. But what they did in this paper is they took the best results for every other method. They took the best performing result. So what we can see is, except for Dyno, where the architecture is a VIT, for all the others, it was a ResNet. So for this paper is the first time where a self-supervised method performs better with transformers. And we can see here the results we get with a VIT S8, KNN score 78.3, that's the highest one. And with a VIT B8, we get a linear score of 80.1. Okay, next I'll pass it on to Tristan to talk about the rest of the results.
Okay, thank you. Let me share my screen. Sorry, I have a little problem. My screen is freezing. So if I start the slideshow. Okay. So what they decided to do is to have more results. They decided to use a series of different tests that they could give Dyno a score and that they could compare to different methods. So the first one they perform is image retrieval. The way it works is we have the Paris dataset here, where we have images of different buildings with a query. And the first thing we have is a medium difficulty data. So we have the same buildings, but with different scales, different viewpoints, different angles, but we can usually see the building pretty well. And then we have a higher difficulty where the building is from far away, it's hard to distinguish, or we can only see a part of it. So in the results, here we can see a supervised approach using the VIT model. And we can see that with medium and high difficulty, the scores are pretty low. And with Dyno, we're able to get maybe 8 points above for medium and 4 points above for high difficulty. Next up, we have a published method for image retrieval using a supervised approach. And this is getting much better results than the Dyno is getting. But however, they also provided a Dyno pre-trained with a much larger data set, and that gave a higher score than the published method with the smaller data sets. Next up, we have copy detection. Basically, we have an input image from a data set that's going to be augmented. So it's going to be rotated, flipped. We can change the scale, we can change the brightness. And what copy detection wants to do is we want to trace back a augmented image to its original input image. out of maybe thousands or millions of input images. So when they scored that, what we can see, we have multiple methods. We have multi-grain, supervised, and Dyno. So we have the architecture, the dimension, and the resolution. So here, if we look at the resolution for 224 square, the best result is with the Dyno method. And if when using a higher resolution with multi-grain, they do get a better result. But with Dyno, when they also augment the resolution size, they end up getting the highest score out of all. Next up, we're going to talk about segmentation. So here we can see an image segmented with supervised approach and with Dyno approach. So over those 5 images here, we can see that Dyno performs much better. As you can see, the elephant is well segmented, the train is well segmented, the bike is well segmented, where the supervised method struggles heavily on doing so. And we can see that in the results. The results are almost twice as high with the Dyno approach, and we can really see the results. So next up, we have video segmentation. Here we have frames of a video where we have a kid on his bike. So the 2 things they're looking at is the region similarity, which is the intersection of a union score, and the contour accuracy, which is how well the contour was drawn compared to the ground truth. So if we look at the scores, if we look at the table we have here, we have a supervised approach, we have different self-supervised approach, and we have a Dyno with different data and different architectures. If we look at the intersection of a union, the highest score is supervised, and here for the self-supervised, the highest score is with Dyno. Then for contour, the highest score is still with this published method here. But we can see there's a pretty large effort from self-supervised method to the Dyno, usually 4 points. And if we mix that together, we see the same results again. And then they did an ablation study. Sorry for that. Next up, we're going to talk about transfer learning, which is another thing they did to test the results of the Dyno. So transfer learning works in a way that you train a model with a large amount of data. And once the model is well trained, they transfer the knowledge to a target model that they're going to fine tune with the target data. So the data that's more relevant to the data set we're trying to predict. So when they did that, we can see scores with 2 different models. So VAT small, VAT large. And we have 2 different methods. So a supervised approach and the Dyno. So, and then we tested that on 7 different data sets. And what we see is 13 times out of 14, the Dyno is getting the better results on transfer learning, which means that it's great for using solving problems that have a small amount of data. And next up, we're going to talk about the ablation study. What an ablation study is when we have a model with a lot of components, we're going to see if I remove the components, how does my results, what results am I getting compared to what I was getting with this module. So the first Dyno method, as explained by Jacob, is that we have a student teacher model that's being updated. We're using global and local crops. We're using cross entropy as a loss method, and we're now using a predictor on the student model. And this is the results we're getting. If I remove, for example, the teacher and the student model updating each other, the model doesn't work anymore. If I remove the global and local crops, I lose maybe 5 points in accuracy. If I change the loss from cross entropy to mean square error, I lose maybe 20, maybe 10, 15 points, which is a very high amount. And finally, if I add a predictor to the student model, I lose a tiny bit of results. So I lose 1% on my accuracy. And comparing that to different models, like the Byol, as explained by Jacob P. earlier, the difference here is that it doesn't use multi-crops, but it uses a predictor on the student model. And we can see the results are 5 points lower than the Dyno method. But an interesting thing is here, if we remove the predictor, we get lower scores, where with the Dyno, it's adding the predictor that gave lower score. And finally, I want to talk about different batch sizes. So here what they showed is a 2D graph where on the y-axis we have the accuracy obtained by the model. On the x-axis we have the throughput, so which is the speed at which we can process images. And here we have two different transformer models. What we can see on both of them is that the higher accuracy is given using the smaller batch sizes. However, they're much slower, maybe 500 times slower than a larger batch size, as we can see here with 16 by 16. And that's the same for both transformer models, is if we use a larger batch size, we lose in accuracy, but we win in throughput speed. And that's it for us. Thank you for watching.